All right, so yesterday we were talking about the universal wave equation, and we were talking about the relationship between the speed of a wave, the frequency of a wave, and the wavelength of a wave. Which one of those three things can't change? Right, the frequency of a wave can't change, which is why we have the formula that we have. Okay, V equals F times lambda. That way, we were saying, if we're solving for F and we know F can't change, if the speed of a wave changes, then the wavelength of a wave has to change as well. And they have to change in exactly the same way in order to preserve the ratio between them and make sure that frequency does not change. All right, that was kind of the big message from yesterday. Now, it's not a difficult formula to use. Okay, and I think at the end of the day, I told you one of the few tricks that you could encounter, okay, with a universal wave equation question was if someone told you how many crests went by or how many troughs went by. Okay, so if they say, you're sitting in a boat and you count 4 crests going by, how many waves is that? 3. Okay, because you start counting on the first crest. Okay, you only make 3 complete oscillations. That means you only saw 3 waves, even though you saw 4 crests. Everybody follow on that? Okay. The other thing that can come up is sometimes a question will tell you you're dealing with a certain kind of wave and not tell you its speed. For example, a radio wave or an electromagnetic wave, which all travel at what speed? Light. Yeah, they're light waves, so they travel at the speed of light. So anytime a question says electromagnetic wave, radio wave, microwave, gamma ray, whatever, okay, all of those things are light waves, and thus they all travel at the speed of light, which is on your formula sheet under other useful constants. Okay, it is 3.00 times 10 to the 8 meters per second. All right, so sometimes a question will just say that, and it's expected you know that they're a light wave, and that's how fast light travels. Same thing. Yeah.
And will be the same like with sound waves?
No, sound is different. I'm going to show you that one right now. Okay. For sound, okay, we've already said that a wave is influenced, a wave's speed is influenced or controlled by the medium in which it is traveling. Any property of that medium changes, the speed and wavelength of the wave will change as a result. Sound is no exception. Light is no exception either, but sound isn't either. So on your formula sheet, you will see this formula. V equals 332 plus 0.6 T. This formula calculates the speed of sound in air at whatever temperature you are given. Big T in this formula stands for temperature, and it's in degrees Celsius. Okay, so 332 is the speed of sound in air at 0 degrees Celsius. Okay, so at freezing, sound travels at 332 meters per second. All right, and then it changes by 0.6 meters per second for every degree Celsius change. All right, that's what this formula will calculate. So it even works if it's below 0, because if it's below 0, T will be negative, and you'll actually be adding a negative number, and the speed of sound will go down. All right, so this formula calculates the speed of sound in air at whatever temperature, and sometimes you'll encounter a question and it'll say, what's the wavelength of these sound waves with this frequency, if the air is this many degrees Celsius? And so you'll have to calculate the speed of sound in air using that formula. Okay, so that's what it calculates, speed of sound in air at whatever temperature you are given. Okay, with me on that? All right. Again, these questions aren't hard. Those are about the only ways we can trip you up on a question like that. Okay, so if we're dealing with like a sample problem here, this would be about as easy as they would get. I have a sound wave with a frequency of 262 hertz, and it has a wavelength of 1.29 meters. What's the velocity of the sound wave? Well, okay, I just plug into my universal wave equation. V equals lambda times F. Okay, they told me lambda, they told me F. All right, all I have to do is plug in the numbers, and I'll get that this thing is traveling at 338 meters per second. Okay, everybody all right with that? All right, so we'll go over a couple examples here and just make sure we kind of understand how this works. Okay, so to generate waves in a stretched spring, you oscillate your hand back and forth at a frequency of 2 hertz. All right, so they gave me F, 2.00 hertz. The speed of the sound waves in the spring is 5.40 meters per second. Okay, what is its wavelength? All right, so looking for wavelength. V equals F times lambda. Okay, if I want to get lambda by itself, I divide both sides by F. Okay, and so I will have 5.40 divided by 2, okay, which should give me 1.7 meters. Sorry, 2.7, not 1.7, 2.7 meters, okay, as my wavelength. Okay, pretty easy. Okay, one other trick that can come up, echoes. Okay, sometimes a question will be set up and the context of the question will be an echo, and it'll ask you to use V equals D over T to solve for the speed of the waves. And it'll say something like this: you shout at a cliff, which makes you look crazy, but you're doing it because, well, the cliff's in your way. So you shout at a cliff and you hear the echo of your shout 2 seconds later. The air temperature is 20 degrees Celsius. Calculate the wavelength of the sound, okay, or something like that. Okay? So you'd have to use V equals D over T to calculate the speed first, and then you'd use universal wave equation after that. What's the problem with an echo question? Okay, if I told you that sorry, I gave you the temperature. I shouldn't have given you the temperature. Let me just write one out so that it makes more sense and I can collect my thoughts. Okay, let's just have you guys write this one down. Yeah. The echo 4.2 seconds later. That should work out. Okay. Okay, so this would be an echo context question. I tell you, you shout at a cliff. I tell you how far away the cliff is. Okay, I tell you how long it takes for you to hear the echo, and then I tell you the frequency and ask you to calculate the wavelength. All right, if I have frequency and I'm looking for a wavelength, what else do I need? I need V. Okay, so can I calculate V if I have distance and time? Yes. What's wrong with the situation? What is a likely mistake I might make? Not doubling the distance is exactly right. Okay, how far does the sound travel? Twice that distance. Or I do what with the time? Divided by 2. Either way will work. Okay, you're either dividing the time by 2 and calculating how long it takes the sound to get to the cliff, or you're doubling the distance because the sound travels there and back. Either way will work and give you the right speed of sound in this situation. But you have to remember that this is an echo, and that's what people forget. They read a question like this without thinking about it, not forgetting that it's an echo, and they go 675 over 4.2, and they get a ridiculously small speed of sound, and then their answer is wrong after that. Some of it, yeah. But I mean, the only reason you get an echo is because the sound bounces off of it. Yeah. All right, so I need to calculate the speed of the sound by going V equals D over T, okay? So what I will do is I'll take the 675, but I'm going to use half the time, okay? So I'm going to go 675 meters. It only takes 2.1 seconds for the sound to get to the cliff. All right, so my speed of sound is 321.43 seconds, or sorry, meters per second. So it's cold. It's obviously below 0 on this day because I just made up the numbers in my head. Okay. All right, so I've got my speed of sound. Now I can use V equals F times lambda and calculate lambda. So lambda will equal V over F. taking my 321 or whatever it came out to, yeah, and dividing that by 700 hertz. All right, so we got divided by 700. Okay, so the wavelength of that sound is 0.46, 0.459 meters. No, 0.46. Sorry, I have two significant figures here. All right, everybody okay with that one? Meters.
So lambda is the distance between the two crests of a wavelength?
Right, lambda is the distance between any two equal parts of a wave, right? So one crest to the next crest, one trough to the next trough, anywhere along, right? I think I showed you guys that when I did the line, right? Okay. All right, so that's a typical echo type question. So you could also have like situations that would involve like light reflecting off of something, okay? Or you could have like sonar. Sonar would be another one, okay? That's a common context, okay? Using sonar means you send sound waves and they echo off something below you in the water, okay? And they come back, right? That's still an echo.
Echo question or something like that. That's like the sound travels a total of 1,300 meters, and that's like.
Yeah, it could be. Yeah.
That's counted within there.
That would, yeah, but it would specifically state this is there and back. I don't remember ever making up an echo question like that because that eliminates the mistake most people would make.
For the light question, would you just use the constant velocity, or would you have to calculate?
No, if it doesn't say otherwise, you use the 3.0. Okay, any other questions on that one? All right. So let's have you guys try number 2 because that's like what we just talked about here. I'll make it bigger so you can read it. Let's actually have you try 2 and 3. Right, give you a few minutes on that one. Okay, so for number 2, okay, we're being asked to find out how far away the rock face is. So we're looking for the distance. Okay, in order to get distance, I'm going to need speed, which I also don't have yet, and time, which I do have. Okay, it tells me that the wave bounces off the rock face and returns in 8.5 seconds, which means how long does it take to get to the rock face? 4.25, right? So I'm going to use that time instead. Okay. If the wavelength of the sound is 4.71 meters, so they tell me lambda, and they tell me the frequency is 325 hertz, okay, then I have enough information to get V using the universal wave equation, and then I can use V to get D after that, right? Everyone okay with that process? All right, so V equals F times lambda, so I'll take my 325 and multiply it by 4.71. Okay. So we got 325 times 4.71. All right. Is that fast? Yeah. Sound travels way faster in water than it does in air. Okay, like 5 times faster, okay, in water than it does in air, right? The more dense the fluid, typically, the better sound travels through it, right? So air is actually one of the worst things for sound to travel through. It travels really slow through air because the particles are really far apart, and it's trying to compress and rarefy them and make the wave travel that way. The more dense the particles are, the better that process works. Transverse waves are the opposite. Transverse waves travel really poorly through fluids and solids, okay, but really well through things that are like less dense. Okay, so we got 1530.75 as our speed. Now we can do a V equals D over T calculation. D equals V times T, and that will get us the distance to the rock face. Again, I'm using not the total return time, but only half of it because I don't want to know how far it is there and back. I want to know how far it is just to the rock face. Okay, so I'm going to take that number there and multiply it by 4.25. So this part of the ocean is pretty deep, in so much as it's 6.5 kilometers deep. So I don't know, it's like the Marianas Trench or something. Okay, it's like really, really deep. All right, how many people are working on 3 still? Okay, so I'll give you a little bit more time here on number 3, and then we'll go over that one. Okay, so we got this boat that is 250 meters from shore. Okay, so we're gonna write that's probably a distance, probably 250 meters. Okay, the dinghy rises and falls 8 times per minute. What did they just give me there? frequency. Okay, it's cycles per time interval. Okay, if they gave you period, it would have been this many minutes to go up and down. Okay, so this is frequency, 8 times per minute. Okay, he finds that it takes a wave 3 minutes to reach the shore. All right, so that distance and that time probably go together. That'll get me the speed of the waves. All right, I'm going to convert this 8 times per minute into hertz by dividing by 60. All right, so there's my frequency in hertz, 0.13. Okay, 0.13 hertz. All right, so we're looking for how far apart are the wave crests. In other words, we're looking for the wavelength. So I'm going to calculate the speed because I have the information to do that. Okay, 250 meters divided by 180 seconds. All right, so I'm looking at 1.38 repeating meters per second for my speed. Now I can calculate lambda. Lambda will equal V divided by F. So I'll take my 1.38 and divide that by 0.13. Okay, so these are pretty long waves. All right, so these waves are 10.7 meters long. Actually, we only have 2 significant figures, so 10 meters long. Actually, no, they should be 11. It should say 11. So they made a mistake on that, but that's fine. Okay. All right, everybody okay with that one? All right. So sometimes you have to read the question pretty carefully in order to figure out, okay, I've got this, how do I get to what I need? And really that's the only, again, one of those ways they can trick you, okay, in a question that's otherwise pretty mathematically easy.
What was the question where you have to use like one less of the wave?
If they said this many crests go by, or this many troughs go by, this time it said he went up and down 8 times, so that's 8 oscillations, right? If they said he saw 9 crests, that would be the same thing. Okay. No, we don't need to do those ones. And we'll skip that one too. Okay, I'm going to have you work on a couple out of the